When we speak, no matter what language it is, we use body parts such as tongue, lips, palate, pharynx. These body parts, they move and we produce certain sounds. These parts are called articulators when we talk about speech research. Hello, I am Prabjot Kaur and you're listening to Social Robotics Talk. In today's video, we are going to review a paper called ArticulateX that was published in Interspeech 2025 recently. We won't be implementing this paper because there is no open source code that's available, but we want to review this paper to understand what is the state of the art in speech research. Now let's dive deeper into this paper. So this paper falls under the same category of speech research that we have studied in the past in this YouTube channel. So mainly speech-to-speech translation, which means there is no text involved when we are doing the translation for speech from one language to speech in another language. So previously, we really went in depth when we did the speech to unit translation. So in this case, in this paper, the authors go from speech to what they call articulator space. Here, when it says articulator space, it comes down to sounds in the speech. So not necessarily the words, but the sounds. So here we go from speech in one language to some sounds in the target language first. Okay, and then they say this is the first non-autoregressive direct speech-to-speech translation model. Non-autoregressive, what does that mean? Well, to understand that, let's understand what are autoregressive models. So let's say you have a model that generates text. In order for that model to generate text, it's generating like one word at a time. So these autoregressive models, they look at the words that it previously generated in order to produce the next word. So those are autoregressive. Now non-autoregressive would be the opposite. So here, in order to generate the next word, the model does not look at what it had generated previously in the sentence. So this is non-autoregressive. Architecture that we have in this paper, it consists of three parts. So here you have a speech to articulator encoder, and then you have articulator to MEL spectrogram, and then you have MEL spectrogram to speech, which is done by the vocoder. So these are the three parts which we will study in detail. And the authors also say that the main innovation of this paper is the speech to articulator encoder. So we'll study that as we go deeper into the paper. And then the authors use this CVSS dataset in order to experiment and show us the results of this architecture. And they say it produced a higher Bill score for their experiments, and they tested for two pairs of languages, one going from French to English, and then the other one is going from German to English. Next, in the introduction, here we have already talked about it. So articulator space is the sound space essentially. ArticulateX models speech as a universal set of articulatory movements, abstracting away language, and that's what we just said, that this operates in the sound space, which comes before we produce a word in any language. And then here again, we just said, so what's happening is you're taking the source audio, and then you're converting that to the sound in the target language, which here they call target articulator. And then we need to convert that sound to a MEL spectrogram. And then finally, MEL spectrogram gets converted to a speech in the target language using vocoder. The key innovations here are, so they have a novel speech-to-speech translation framework, which takes advantage of the intermediary sound units. So it's language agnostic because we are just talking about the sounds Although I would say that in some languages you have sounds that are not present in other languages. So I wouldn't say it's completely language agnostic, but to the most extent, it is language agnostic. And then they say we present detailed methodology of mapping acoustic signals to articulatory representation using deep neural networks, and then they provide experimental evaluations. Moving down to the crux of the paper, ArticulateX. It consists of three components: speech to articulator encoder. Let's study that in a little bit more detail. So this speech to articulator encoder, it takes the speech in the source language and then it produces articulatory features, which are essentially the sounds in the target language. And how it does that is by putting together three things. So we have a feature extractor first, which is followed by a conformer block, which is followed by a sparse transformer. So essentially, you are taking a raw audio and then putting that through a feature extractor, which we'll look at the details in just a minute. And then you are taking the output from the feature extractor and putting that through a conformer block. And they're using 4 conformer blocks. So what is a conformer? It's a different architecture, and there's a whole paper about it, which I covered in the previous videos, and I'll link that video here if you're interested. So this conformer, essentially for the purposes of this video, we can say that this is just another encoder that consists of parts of transformer and a CNN. So it's an encoder in itself. The output from this encoder is then passed through a sparse transformer. Sparse transformer is actually your original transformer, but the attention mechanism is sparse. So if you recall, in the transformer, we have an attention mechanism where every token attends to every other token in a sentence. In case of sparse transformer, every token does not attend to every other token. So the attention mechanism in this sparse transformer is different than the original transformer. And there is also a paper that describes this architecture in detail. I'll link that paper in the description as well. So all of this, what you get from here is the source speech goes in and you get the encoded output, and that encoded output basically are the sounds in the target language. Now let's look at these components in a little bit more detail. Here we have a source speech that goes into a feature extractor, which is nothing but 1D convolution layers, and then you have a leaky ReLU as the activation, and then output of that goes into a conformer block, and they're using 4 conformer blocks. Out of this you get something that is encoded, which goes into the sparse transformer, and sparse transformer, as you can see, is nothing but the transformer with the encoder and the decoder. So this is what we get at the end, which are the articulatory units or sound units in the target language. So once this is produced, then this gets fed into the second block of the architecture, A2ML generator, because you want to eventually generate the speech in the target language. So here they're using spectrograms as an intermediary output and then converting those spectrograms to speech using a vocoder. So this is the overall architecture. Okay, there is more details here and you're free to read them. But let's move on to the next section, which is experimental setup and results. For experiments, they used the CVSS dataset, which is a parallel speech dataset. So you have parallel speech, you also have parallel text here. And they experimented with 2 pairs of languages going from French to English and German to English. In order to train the model, we need some training data. If we look at their architecture here, the first encoder, speech to articulator encoder, what you are training is you're training it to go from the speech in the source language to articulatory units in the target language. So you need that data for supervised training. You need those pairs. I didn't find sufficient information in the paper for me to fully understand how they're producing those articulator units for training. So I wish I had a little bit more detail there in the paper, but I'll try to explain based on what I understood from what we have here. So they're saying the target language is converted to sequence of phonemes and which are then converted to binary encoded articulated feature. So they are taking the target text in order to produce the training data. They're taking the target text, converting that to phonemes. Phonemes are again sound units, and those are binary encoded. So this is the set of features that they are using to represent the target language during the training phase. So we have two pairs. On the source side, we are taking the raw audio, and on the target side, they are using these features during the training phase to train this speech to articulator encoder. So that's my understanding of, of how they're producing these features. And then other configurations of the training are standard stuff. Then finally for the results, they say that for the languages that they tested, they got higher Bellevue score and they compared those results with other methods. From here, you might be familiar with Translatotron 2, which I had covered in one of my previous videos. And then you are, I'm sure, very familiar with speech-to-unit translation model, which I heavily covered in my videos before. So they compared the results with those, and they are saying that their model gave them better results. And then here is paper is talking about the ablation study. So in the ablation study, they study like if we replace the speech to articulator with different things. So here they're going from articulator to articulator. So it's going from articulator in the source language to articulators in the target language. So if you use that block, then what do they get? And then here they're using the text in the source language to articulator in the target language. And then they're giving you the results, what they get. And then this is what we have learned just now, going from speech in the one language to the articulator in the second language. So this is just showing that the configuration where you're going from audio, the source language, to the articulator space, that that component gives you better results compared to these two configurations. Basically, that is the architecture that is presented in this paper. So let's just go back to recap, and I'll be quick. So in this paper, the authors present direct speech-to-speech translation model, which means there is no text involved when you are translating from speech in one language to speech in another language. And this model has three components. I think they had a better picture here. Three components. So you have a speech to articulator encoder, which is composed of three other things. And the output of this encoder goes through to convert that articulator feature to a MEL spectrogram. And then finally, the MEL spectrogram gets converted to the target speech. So this is the architecture. And also the paper says that these components, if you want to replace it with other components, the pipeline allows you to do that. Yeah, so that's the paper. So once again, I wish there was more detail about how they are producing these articulatory features to train the model. I think that would have been helpful. But overall, it's good to know where the state of the art is in terms of speech translation research and where it's going. With that, we will conclude today's video, and I'll see you in the next video. Thank you.